If you're an elephant, then you can learn how to fly. Before we start talking about that, let's have a look at another logical implication. There are cards having on one side a letter and on the other side a number. Someone looked through the cards before and said, if one side of a card has the letter D, then the other side has the number 3. Now look at these cards. Select the smallest number of cards you need to turn around to verify the rule. You may pause the video to make your choice. Remember, you want to turn only the cards that are really needed to check the rule, not those that are irrelevant. If you have selected the card showing D and 3, you have selected as the majority does. It is incorrect, but no need to feel bad, it's only human. Only people who have seen this problem before, or those who are specially trained and took the time to think, answer correctly. The correct answer is D and 7, and I will show you how. You really need to check the card with 7 on it, and as if it had on the other side the letter D. The rule, if one side of a card has the letter D, then the other side has the number 3, is broken. This card does not have the letter D on the other side, so all is good. Now you do not need to check if there is D on the other side of the card showing 3, as it does not matter. This card does not have D on the other side, it is the letter M. But the rule did not say what number the other side of such a card should have. For the same reason, you do not care to flip the card showing K on it. Finally, you do need to turn D card, as there must be the number 3 on the other side, which is not, so the said rule is false. Only about 10% of people select the correct option in this abstractly formulated task, but the number will go much higher if we put a social context to it. Here is a new rule. If it rains, then I take my umbrella. And the cards are rainy, sunny, have umbrella, no umbrella. As before, select the smallest number of cards you need to turn around to verify the rule. Of course, you all got it right this time. I have my umbrella with me, it does not rain, and this piece of information does nothing to the validity of the rule. You would only care if I didn't have my umbrella and it was raining. So why the most of us were looking at what would be equivalent to people having an umbrella in the original problem? Because seeing me with umbrella, it makes it more plausible that it rains. It does not imply it, but seeing more people with umbrellas just adds to the evidence. So we have learned that the logical implication, yes, symbolically expressed by an arrow, thanks Math Elephant, is false only if the premise A is true, while the conclusion B is false, although this has another dimension in our daily life. Armed with this knowledge, let us analyze some other logical implications. If an animal is an elephant, then the animal can learn how to fly. This implication is clearly false. Elephants cannot learn how to fly. An animal can be an elephant, so the premise can be true, but the conclusion is then false. Let's have a look at another one. If an animal is a bird, then the animal can learn how to fly. This is still false, because the premise is true for penguins and ostriches, but they cannot learn how to fly. Now consider this. If an animal is an elephant, then the animal can learn how to paint. Finally, this is true. Do you not believe me? Here is a painting done by an elephant. Amazing. An elephant did it in front of my naked eye. Elephants are amazing. Now we are ready for the big one. If you are an elephant, then you can learn to fly. This one is true. Whoa, wait a moment. Are you serious? Well, by you are an elephant, I mean you. You are not an elephant. Sorry, you are a human. So the premise, "you are an elephant," is always false. And since it is false, you do not care whether the conclusion is true. Like you did not care whether I had my umbrella when it was sunny. Okay, a pathological case, surely. What do you know? In mathematics, it is really used in that way. A prime example comes from the set theory. We say that a set A is a subset of a set B. If an element is in A, then it is also in B. An empty set does not have any elements. So being an element of an empty set is always false. Hence, this implication is always true for an empty set, and an empty set is a subset of every set. It would be deeply troubling if a single contradiction, a statement that is always false, was proven in mathematics. It would then mean that everything can be proven, making mathematics utterly useless. Disturbingly, it is not possible to prove that this is not the case within the Zarbelov-Frankel set theory, which is considered the foundation of current mathematics. But the situation is not as hopeless as we can still prove relative consistency of mathematical theories, and we feel assured that mathematics is contradiction-free in general by firmly connecting it to the real world, where we have not yet observed any contradictions. On the other hand, constructing contradictions is one of the most powerful tools in mathematics, assuming its consistency. Since contradictions are not allowed, constructing them allows us to infer the negation of what was used to construct them and what was not yet known to be valid. Here is a symbolical expression of this procedure. A was not yet known to be valid, but it was used to construct a contradiction, and thus, it is the negation of A that must be valid. Thanks a little bit for explaining the symbol. For example, we may assume that the square root of 2 is a fraction. Since this is equivalent to 2 times q squared equals p squared, it must be that p squared is divisible by both odd and even number of 2's, a contradiction. Thus, the square root of 2 must not be a fraction, it is an irrational number. Now, anyone who believes in the classical logic will note that due to the double negation law, this proof of negation is equivalent to the following proof by contradiction. Symbolically, the negation of A was not yet known to be valid, but it was used to construct a contradiction, and thus it is the double negation of A, logically equivalent to A, that must be valid. For example, assume that no irrational number raised to an irrational power gives a rational number. If this is true, the square root of 2 raised to the square root of 2 is an irrational number. Similarly, the square root of 2 raised to the square root of 2 raised to the square root of 2 is an irrational number. Now this is clearly false, as this number is 2, a contradiction. Thus, there are a pair of irrational numbers that one raised to the power of other gives a rational number. Nevertheless, intuitionists would have a problem with this conclusion. For them, the double negation law is not acceptable, neither the proof by contradiction. Intuitionists would point out that we have not actually constructed an example of 2 irrational numbers giving us a rational number when one is raised to the power of the other one. To be more precise, from the proof above we do not know whether the square root of 2 raised to the square root of 2 is rational or irrational. Intuitionistic logic is weaker than the classical logic. It can prove less, and although large parts of mathematics were built on intuitionistic foundations, we usually think in the classical logic when doing mathematics. This is true even when we analyze intuitionistic logic itself. On the other hand, the importance of intuitionistic logic is that it allows its proofs to be rewritten as algorithms, which is known as Curry-Howard correspondence. Computer scientists are often the biggest supporters of intuitionistic logic for this very reason. And this also allows computers to assist with proving theorems. The first theorem that was successfully proven only with aid of computers was the 4-color theorem. The theorem says that any map can be colored with only 4 colors, so that no 2 neighboring countries, which means 2 sharing an edge and not just a point, have the same color. If you are a human, then you cannot check the proof. But if you are an elephant, then, logically, you can.